So let's first interpret. So first of all, I forgot a 4 in there. So it says 2L and then there's a 4. I just wrote this 4 in the break, so just in case. Okay, in the notes it's in there. So let's first try to interpret this and see what are the consequences, and then we'll try to see where this comes from. So let's first assume that the dimension is fixed. So d is fixed and n goes to infinity, right? Then what do you see? You see that the loss, the average loss, is at most twice the loss of the best thing that we could have knowing even the distribution, right? So which we don't know. So that factor 2 is not very bad. Plus something, and I have 1 over n to some power in there, right? So if n goes to infinity, this goes to the whole thing, 1 over n to this power goes to 0, right? And so this means if d is fixed, right? So d fixed, n tending to infinity, right? We get an upper bound 2 times, at most 2 times optimum, loss of optimum. And the optimum had much more knowledge than we have. So that's pretty good, right? So that's good news, right? We're happy with that. Okay? But unfortunately, this is rarely the case, right? Unfortunately, more case is that maybe n fixed or maybe slowly growing right? And if d becomes large, right, that's very bad news, right? Because of course this is a bound, so we should be careful in interpreting it. This is not an equality. So the bound simply might be bad, okay? It might not just be that it's really that bad, it might just be that the bound is bad. But if we take the bound literally, right, then what happens is, unless, if we want this right-hand side to be just some constant, let's say some alpha, right? So unless n grows exponentially, so something like 1 over alpha to the d plus 1, okay? So 1 over alpha is something larger. So unless it grows exponentially in d, right? Then the n to the, 1 over n to the 1 over d plus 1 will go to 1. Okay, so we'll go, so this will become, basically you don't get anything here. And then in front you still have, of course, this extra factor d. Okay, I don't write it here now because the extra factor squared of d grows much slower than this thing here, right? These are all exponential, so these are the determining terms. But so it means then the bound will become completely useless. Okay, there's nothing we can say. So unless we have an exponential growing data in a dimension, then at least according to the bound, we don't hope to get something very good. Okay, and again, this is a bound, so you might be saying, well, maybe perhaps it behaves better, but you do see that actually when you're trying it out. Okay, so that's just interpreting it, that small dimensions, large data, good, whatever data, large dimension, bad. Okay, so that's our take home. So now, how do we analyze it? So how do we go about it? So imagine that we do the following. So pick ST randomly, but only reveal the xn. So someone picks for me the whole set ST, but only then reveals to me the x right now. The labels I don't reveal. Okay, then pick extra sample, so a new sample, x, y, but also only reveal x. So again, I don't reveal the y right now. Okay, I just want to reveal it a little bit later. Okay, because then it will be clearer to see what's happening. Okay, and so this is something called the principle of deferred decision. So sometimes in probability, it's easier. There's many ways of how you can think about how an experiment is set up, and sometimes it's cleanest if as you go through the algorithm, you always just reveal what is necessary at this point, because it's then kind of clear that all the other stuff you haven't used. It just makes it clearer, you know, that things are, let's say, independent of what you have used beforehand. Okay? So now find the neighborhood. So let's say, you know, this is the closest x prime in ST to x. Okay, so find the guy that's the closest to this set. Okay, so in pictures, I pick these points here, but I don't tell you, I don't make a color because I don't tell you yet what they are. Right, and remember everything is in this unit box here, but I don't know what the distribution of this thing is. X, they could all be in the left side corner. They could be uniformly distributed, I don't know. And now, so I don't know what color they are yet. And then I pick an extra point here. And now I find my closest neighbor, right? That I have. Okay, so now I have these 2 points. Maybe let me just, because I don't know what I used in the thing, let me just call them slightly different. Okay, it's okay. So now I have 2 points, right? I have a point x, and I have another point x, x, what did I call x prime, right? So I have these 2 points. Okay, now I'm going to look at the y labels. Okay, so now I will ask for the x and the x prime to reveal to me what the actual y labels are, right? So the x lives in the is this new sample, and the x prime was an element of the data sample. Okay, so now reveal x and x prime labels called y and y prime. Right? And so now I'm asking, what is the chance that the 2 are actually correct? Right? So that I'm actually, you know, because the 2 are the same, not correct, that the 2 are the same. Why I'm asking that the 2 are the same? Because in my prediction, I will take this label here, right? And return the label of this one. But there's a real label attached. Oh, sorry, the other one. This is from the ST. In my prediction, I will take the label from here, right, and return this. But there's an actual label attached to here, and that's the truth, right? And I'm asking, what's the chance that they're the same, right? Good. So I hope that that's clear. That that's exactly the probability of if I'm looking now at the loss. If I did now this experiment many times, that would be the loss that I'm experiencing, right? So, okay, so now let's do first something simpler. These 2 points will not be, of course, spatially the same. So let's first assume that these 2 points actually coincide, okay? They're the same point, okay? So what this means, really, what I really want, is that associated to these points are probabilities of getting 1, right? So I have associated to these points are the eta of x and the eta of x prime, right? So remember what this was. This was the probability that y is equal to 1 given that I have x, and that's the probability of y is equal to 1 given that I'm sitting at the point x prime, right? So for a second, assume for a second that these 2 probabilities are the same and equal to eta. Okay, of course they won't be, because they won't be at the same, these 2 points won't be identical, but just to keep things simple right now. So if these are the same, then since we revealed things afterwards, right, then what I do is simply the following. For one point, I simply ask, give me the label, right? And the label is a probabilistic function. It's not, there's no deterministic one, right? So this will give me, with chance eta, it will give me 1. And with chance 1 minus eta will give me a 0, right? And now I do it again, independently, right? And I'm asking, what's the chance that the two are the same? Right? Take like a coin. The coin gives you 90% heads and 0% and 10% tail. You flip twice the coin, these are independent trials, and you ask, what's the chance that both times you get the same thing? It doesn't matter whether it's 0 or 1, but we want the same. What's this probability? Or what's the probability that they are not the same? We are interested in the probability of error. Well, it can happen the first time I get a head, and the second time I get a tail, right? Or it can the first time I get a tail, and the second time I get a head. So written in terms of eta, that is? Right? So let me just write it as not. Right? So this probability is 2 times eta times 1 minus eta. That's the error. That's the error probability. Probability. Is this clear to everyone? Right? Eta is the probability I get a 1 in the first time. 1 minus eta is the second time I get a 0, right? But I could also get in the first time a 0, which is 1 minus eta, and the second time a 1, which is eta. So, and both of them give me an error. So that's why it's 2 times eta times 1 minus eta. Good. So, okay. So that would be it, right? So in principle, that would be the error probability if I knew the x, if I knew exactly, if the point that I return, so if I had basically an infinite density, so there's a point that's exactly the same point that I'm asking for, and I had a sample for that point, that would be the error probability, right? But now we have to pay a price because we don't have a point that's exactly the point we're asking. We can only ask a neighboring point. Is that clear? So now we don't know exactly what this, these two coins, it's like now I have one coin that has a certain probability eta, and I have another coin that has a probability eta prime, right? And now we do the experiment again, right? And so now I'm asking what's the chance that these two things, and I'm estimating one by the other one. Okay, so now the problem is the following. So if I do this now with an eta and an eta prime, okay, if these are now not the same, then what is again the probability of error? Well, it will be eta times 1 minus eta prime, right? Plus eta prime times 1 minus eta. Right? Is that clear? I can do a 1, 0, or a 0, 1. That's it, right? And now what I want to write is, so now I want to, let's just check. So I want to see how much different is this from the other case, okay? So I want to write this as 2 times eta of 1 minus eta, like the case where I know what's going on, right? And then plus something, right? And so the claim is that I can do this, and that I can write it as eta prime minus eta. Okay, so let's just quickly check that. Okay, so the claim is that this probability I can bound by the actual probability, right, that it's at some point that I know, plus how different these two etas are, right? And so now, of course, then the idea will be that this is 2 times eta, 1 minus eta, plus, and a plus, and now if this of x minus x prime. Right, so now I use my Lipschitz thing here. Okay, so from here to here, okay, so now, maybe we'll see how much time we have. Let me just write down here so what you should get here is 2 times, it's 1, I think you get 1 minus 2 eta times eta prime minus eta. Okay, so that's the bound That's the bound that you actually get here. And this bound you just get by taking this, subtracting like this, and then seeing what is the difference. And that difference should be that. Okay? Maybe when we have time, we can still go back and do that. Okay? But then since eta is between 0 and 1, right, then this thing here in absolute value will also be between 0 and 1, and then you have just this left. Okay? So that's how the bound comes about. Good. So our probability of error is upper bounded by this. Okay? But now we are actually very close. Okay? So why are we very close? Because now I still need to, of course, take, so this eta here, of course, still depends on my point x that I have, right? So if I averaged it out, I would get x. But I want to now relate it to my probability of error of the optimum guy. What was the probability of the error of the optimum guy? So I should now take this, right? And I should now take the expected value over the x, everywhere there's an x inside here, right? Because these points depend on the x. And of course, this depends on the x and this depends on the st, you know, the set that I have, right? So this will look already like what we have up there. But what was the error for the optimum scheme? This will give us the error, you know, here this will give us, from this will be the error of the optimum scheme. But it doesn't quite look like that, right? What was the error of the optimum scheme? We wrote it down somewhere. Maybe I erased it. Okay, I don't know, maybe it's written. I don't know if we still have it. Oh. Not sure we have it written there, right? So we have it written in the middle. The error of the optimum scheme was equal to the expected value, right? And so instead of having the product of eta times 1 minus eta, we have the minimum between eta and 1 minus eta, right? So what's the relationship between them?
Like this one is less than a meter.
Right, so because, right, so what happens here is that let's assume the minimum is eta, right? Then this will still be a number smaller than 1, right? So forget about the 2. So this thing here, the claim is that this is less than 2 times the minimum of the eta and 1 minus eta plus the c. Clear? Right? Because I just multiply with an extra number, right? But so now, if I'm taking the expected value over everything, right? So now, take the expected value here over, so everywhere is now an x, right? So let me maybe write down the final inequality and then put the x's in there. So what I just proved is that the eta of x times 1 minus eta of blah blah. What do I have of eta prime of okay, 1 minus eta of eta of x prime, right? Plus eta prime, so this eta of x prime, right? Times 1 minus eta of x, right? And we proved that this is smaller equal than 2 times the minimum of eta of x and 1 minus eta of x plus the c times the x minus the x prime. Okay, but this x prime of x was of course just what we had called before in the neighborhood of the thing of x. Okay, and so wherever there's a prime, that's just the neighborhood here. So now if I take the expected value here, right, so this of course depends again on this neighborhood here. I don't know how to write it now. So I should go over the st and I should go over the x. And so this thing here will be now so this whole thing here is now my expected loss. This is exactly what I was interested in. And so now I also do here the expected value over everything. And I do here the expected value too. Okay, and again, this is again over the expected value of x, and x is value of x, and here again have over the x and the st. Okay, so now this thing here we already know, right? So this we said here is exactly just 2 times L of f star. So we're done, right? And the right-hand side is exactly the term that we had written up here, right? So we know now. And so, you know, the proof is not really a mystery here, right? Maybe what's a little bit curious that we get this term which relates to the optimum way. What's not a mystery is that we get a term that depends on the average. What is this extra term that we have? It's the average distance between the point x that we're given and the closest point that we can find in the space, right? And it's obvious that we should get a term something like this in there, because our only assumption is that there's somehow spatially being close to a point that we know tells us something about this label, right? So we have to get a geometric term like this, you know, what exactly the constants are in front, okay, whatever, right? So now the only thing to still do is to, and that I'll just, you know, explain now roughly. So how do we get now some relationship between, we have this extra bound that we have on the right-hand side, okay? And so if you're interested in the exact proof, it's not super long, but it's slightly longer than what I want to do here. If you look in one of the books, in the Shailev book that's Understanding Machine Learning, you find the exact proof. It's maybe 2 pages or something like this. So I'll just, you know, give you a rough outline of how you get from this to the other one, right? So now the idea is the following. So remember, we always assumed that we're operating in some unit cube of dimension d, right? But we don't know anything about the distribution, right? So we don't know that it's uniform, we don't know. So the idea is the following. You separate out, or you make another grid in there, okay? So it's a grid in all dimension, and I can't draw this, okay, so whatever. And so what it is that we make this into cubes of side length epsilon. And this epsilon will be then later on a parameter that will fix, okay, that will be optimized to get the best bound, okay? And actually you kind of see the epsilon up there. It's exactly this function in terms of the n that turns out, you know, that's related to the epsilon, okay? But right now it's just a box of side length epsilon. Okay, so now there's a certain, so what happens is now is the following. So, you know, take these boxes here and number these boxes from 1 to how many whatever boxes there are, right? I mean, they're 1 over epsilon to the whatever. They're 1 over boxes per thing, and then there are d dimensions. So there will be, you know, so if you take an index 1, I, from 1 to something like 1 over epsilon to the d, that's roughly, you know, that's how many boxes you have up to, you know, things. So take just an index. Every box doesn't matter, right? Now, we don't know what the probability is that if you take box I, you don't know what the probability is that a sample, a random sample falls in there, but let's just call it pi. Right? So, you know, we all know that the sum of all the pi is 1 because the sample has to fall in one box, but we don't know, right? They could all fall, the probability could be all concentrated on one box, could be all uniformly distributed, we have no idea. So what are we interested in, right? Okay, so let's assume I'm in box I. Okay, I have a new sample. And now I'm looking at the rest of the samples. And I imagine now that the rest of the samples are just now revealed to me. This set ST is revealed to me now, right? So what is the chance that one sample of this big sample ST does not fall in the box? Right? So the chance that I imagine, that X given, that's my new sample, falls into box I. Right? And now I imagine I look at all the other n samples that I have, so these n samples from the training set. Now the chance that one of them doesn't fall in there is what? It's 1 minus, right? It's the same that we had already beforehand, right? I mean, there's a chance, 1 minus pi is the chance that it falls outside this box, right? So what's the chance that all of them fall outside the box? Is this, right? That's a chance that inside my box I see nothing, right? That's exactly the same kind of calculation we did beforehand. Now, why am I interested to know that I fall inside the box, right? Because if I fall inside, if I'm in the box and I have at least one guy inside the box, then how far can this guy be away from me? Sorry, epsilon times? I have a box of side length epsilon. So what is if I have two? A box of side length epsilon, and let's assume I have just a square in 2. Then I get the diagonal is how long? Square root of 2 times epsilon. So if I have a cube, the diagonal is 3, right? So in general, right? So if there is a box, if there is a point, at most square root of d times epsilon away. Right? So if epsilon is small enough, d is there, but I can pick epsilon somehow small enough, then I can make that small, right? And if that's small, then we know that I can get a good estimate, right? We know that if that's the case, I can, so that's good, right? Clear? So, okay, fine. So now what happens if I don't know, if I don't find anything in the box? Then, right now we just give up and it could be anything, okay? Could be somehow order square root of d away, of square root of d away, right? So now the problem is, so I could write down now a bound, right, in terms of the pi's that I have here, right? For every pi, I have so what is it? For every pi, I have a chance of pi of falling into the box, right? And then I have a chance of, if it's only of 1 minus pi to the I, of not finding a good guy close enough, right? Not within that thing. Is that clear? So the average distance, let's just write it down. So what would be the average distance? Right? So I have a chance pi to fall in a certain box, the new point. If I fall in this box, right, then if I'm unlucky, right, then if I'm lucky, then I have distance square root of d times epsilon distance, right? If there's another guy that falls in this box. Okay, so, but if I'm unlucky, right, then I get an extra term of square root of d, and with that probability, 1 minus pi to the n. Is it clear? Yes? So if I'm unlucky, right, which happens with that probably 1 minus pi to the n, I get a distance of square root of d. If I'm lucky, right, then I'll get, which, I can put an extra bound here, 1 minus 1 this, but I can bound this by 1. I get this distance here. Everyone with me? That's a bound on the average distance. So now I don't know the PI. What do I do? So the point is that it turns out that we can just kind of think of a worst case. Why? If the PI is small, okay, if I'm in a box that you will never fall into because this box is just a very unpopular box, okay, just like way in the back, okay, nobody wants to sit there, okay, then this term is small, okay, because this is, this is small, okay, but if it's a popular box, okay, then, okay, I always pick up this thing here, right? But then I can make this term small because I have the other term in here because, it's very unlikely, if it's a popular box, it's very unlikely that nobody will be there besides myself. That's the definition of a popular box, okay? And so now what we can simply do is we can take like the worst case, okay? And now optimize over the, whatever, then pick whatever is the best epsilon. And if you do that, you get exactly this bound. Okay, that's it. So, we're done, okay? So let's summarize. We looked at nearest neighbor. In principle, we can do k nearest neighbor. The more k you pick, the more you do smoothing, so the model will become less complex. If k is very small, it can do something very complex. We saw from scaling that as long as your data, either you're in very low dimension or your data scales exponential, then so that you really have very close neighbors, then this is a very good thing because you can do almost as well as having actually knowledge or having access to the distribution, okay, pay at most a factor 2. So that's excellent. But in any realistic scenario where you don't have this exponentially large data, so even for these 10 or something like this, which is not large, you're very unlikely having enough data. And in this case, simply the notion of distance is not very good. If you have enough data, so if you're in low dimension, you have a lot of data, then right now we made an assumption that's only one possible, is that this distribution is smooth, doesn't change very much over the position. Okay, so this means that if I have a sample that's very close to me, then likely the output of that sample will tell me something about what my sample should be, right? And so this bound that we have up here exactly kind of predicts it, right? It says, well, we do at most as bad as the map decoder, base decoder, plus a term that has to do with how close is my closest sample. And we try to, bound here a little bit how close this is, right? And so that gave us the upper bound that we have up here. Okay, so that's all we're going to say about nearest neighbor. Next week, you'll do another linear classifier, which is support vector machines. And at some point later on, we'll do neural nets. And so that will tell you pretty much anything you need to know about classification. Okay, thanks.